Hello. Today we're going to look at the Standard Model. This is a table which sets out the fundamental particles of which we are currently aware, which make up everything else. In my videos on the reason for quantum mechanics, I explained that it was originally thought that the atom was the smallest indivisible thing. But it was subsequently discovered that atoms were made of protons and electrons. Chadwick subsequently discovered neutrons. Protons and neutrons join together to form a nucleus. The electrons orbit the nucleus. But is there anything smaller than these particles? And are there any other fundamental particles? An electron seems to be a fundamental particle. It cannot be divided. But we now know that protons and neutrons are made up of quarks. Each proton and neutron has 3 quarks. There are 2 types, an up quark and a down quark. A proton has 2 up quarks and 1 down quark. The neutron has 2 down quarks and 1 up quark. An up quark has a charge of plus 2/3. A down quark has a charge of minus 1/3. So a proton has a total charge of plus 2/3 plus 2/3 minus 1/3, which equals plus 1. The neutron has a charge of minus 1/3 minus 1/3 plus 2/3, which equals 0. The quark seems to be a fundamental particle. It cannot be divided. There is a theory that everything is made up of strings, which are very tiny vibrating strings of energy, rather like a wobbling elastic band. But there's no hard evidence for that yet. Protons can be converted into neutrons and neutrons into protons by a process called the weak interaction. This simply involves one of the quarks in the proton or the neutron changing from an up quark to a down quark, or a down quark to an up quark. In the case of a proton turning into a neutron, an up quark changes to a down quark. In order to balance charge and energy, 2 other particles are produced. So a proton becomes a neutron, a positron, and a neutrino. The positron is the antiparticle of the electron. We will discuss antiparticles later. Neutrinos are curious particles. They very rarely interact with anything. Millions of them are produced every second in the sun. They travel to Earth, pass right through it, and continue into outer space. Millions of them pass through your body every second without you noticing. Indeed, it is the weak interaction which converts protons into neutrons, which enables the sun to burn and produce energy. The sun, and indeed any star, is fundamentally composed of hydrogen. At the very high temperatures inside the sun, the electron has so much energy that it can escape from the atom, leaving just a proton behind. The weak interaction converts some of these protons into neutrons. Protons and neutrons can then combine to form helium. A helium nucleus has 2 protons and 2 neutrons. But the mass of a helium nucleus is slightly less than the total mass of the 4 particles which make it up. That mass difference is converted into energy according to the formula E equals mc squared, where m is the mass difference, c is the speed of light, and E the energy, which is produced mainly in the form of light and heat. That process is going on all the time and is the source of heat and light from the sun, and indeed the reason we can have life on Earth. So pretty much everything that we observe in the universe is made of protons, neutrons, electrons, and neutrinos. Protons and neutrons are made from up quarks and down quarks. Is that all there is to it? Well, no. For some reason, nature has decided that the most fundamental particles come in 3 sizes. Only the smallest size is stable. The larger sizes quickly decay into the smallest size. The Standard Model is usually presented in a table like this. The first two rows are dedicated to the quarks. The up quark and the down quark fit into the table like this. These are the quarks which are the basic constituents of protons and neutrons. But there are two other quarks which are heavier than the up quark. These are the charm and top quarks. There are two other quarks which are heavier than the down quark, the strange quark and the bottom quark. The next row is given to the electrons. The ordinary electron goes here. But there are two heavier forms of an electron, the muon and the tau. The next row is given to the neutrinos. The ordinary neutrino, called the electron neutrino, goes here. There are then two heavier neutrinos, called the muon neutrino and the tau neutrino. So these 6 boxes consist of the quarks. These 6 boxes consist of electrons and neutrinos, which are collectively known as leptons. These are the most fundamental particles of matter of which we are aware. Everything is made up of these particles. But there are 4 remaining boxes, and these are known as gauge bosons. They contain what are called the force carriers associated with the known forces. We are now aware of 4 fundamental forces: gravity, the electromagnetic force, which is the force which causes charged particles to attract or repel, and which is the source of magnetism; the weak interaction, which I described above, and which, amongst other things, converts protons into neutrons or neutrons into protons; and the strong interaction, or nuclear force, which is responsible for binding the nucleus together to stop the positively charged protons within the nucleus from repelling one another and thus causing the nucleus to self-destruct. The question is, what causes the forces? The idea is that for each force there is a force carrier, something which exchanges information between the particles involved in the force. In the case of the electromagnetic force, the exchange particle, or gauge boson, is a photon. In the case of the nuclear force, or strong interaction, the gauge boson is the gluon. In the case of the weak interaction, the gauge boson can be the Z boson, or the W plus or W minus boson. It is also thought that the force of gravity has an exchange particle, or gauge boson, called a graviton, but so far there is no evidence for that. The mass of the gauge boson determines the range of the force. The lighter the boson, the greater the range of the force. Photons have no mass, and therefore the range of the electromagnetic force is infinite. W and Z bosons are very heavy, and consequently the weak interaction is a very short-range force. As if this were not enough, every one of these 12 fundamental particles has an antiparticle. An antiparticle is the same in every respect as its opposite number, except that it has an opposite charge. So an anti-electron, called a positron, will be exactly like an electron, but with the charge of +1. It does not have a negative mass. An up quark has a charge of +2/3. So an anti-up quark has a charge of -2/3. You rarely see antimatter except in a laboratory. It cannot survive for more than a fraction of a second before colliding with ordinary matter and annihilating it to produce energy, using the term E = mc². It is thought that when the universe was created, equal amounts of matter and antimatter were produced, and that these subsequently came together and annihilated, leaving a small residue of matter, which is the substance which now constitutes the universe. This then is the standard model. Everything that is known in the universe has these elements as their basis.